All right, welcome everyone. How's everyone doing? Everyone good? Nice Wednesday. We're almost there. End of the semester's like right around the corner. So definitely looking forward to that. I know I've been really busy. So for today, we're going to be talking about databases, specifically relational and non-relational databases. There are a ton of different types of databases, which I'll go over, but we're mainly just going to be diving into relational and non-relational. This workshop is going to be a lot more conceptual than a follow-along coding type of thing. It's going to feel a lot more like a university lecture than maybe a YouTube tutorial, right? The reason that I say that is expectations. I want you all to leave this room with the understanding of databases as a concept and an idea. We'll be doing a very small amount of code in the workshop, but being exposed to these concepts is what's going to be able to give you that confidence to approach the actual technologies to program on your own time. Because we don't have enough time to go through all of that in the workshop window that we have. So I kind of dive into the concepts. You guys can kind of take it from there, and I give avenues to go ahead and explore that on your own time.
And also, plus side, coding databases is not that hard.
Yeah, okay, perfect. I'll go over into that too. So kind of just the overview of what this presentation is going to be. First, we're going to talk about why do we use databases. Feels like an obvious question, but there's a lot more than you might not expect. We're going to talk about NoSQL versus SQL. Then we're going to define each of them in their own contexts. And then we're going to talk a little bit more about SQL. I'm going to be diving in deeper into SQL because at the end of the day, there isn't too much complexity to NoSQL databases. You can kind of just intuition your way through that. So I'm going to talk a little bit more about SQL stuff and then show you some stuff at the end. So to get started, why do we use databases, right? So if you guys have learned to program without YouTube tutorials and kind of just, the way I did it was I would just brute force everything. I'll just try to kind of make my own little clever approaches to things and horrifically crash and burn by doing the dumbest thing possible. So one of the approaches that I feel like is very intuitive is to just use a JSON object and write it on your system wherever your application is stored, one big JSON file, and you could either put that on the server and read it through the API on the server or whatever you want, but there's a lot of drawbacks to one big JSON. So one of the reasons we use databases is the very important one is data persistence. If something happens, your database is a lot more fault tolerant than a JSON file. For example, if the power goes out while you're mid-write on a JSON file, it could corrupt the file. There's a lot of persistence issues and security issues with just doing that approach. On top of that, you have that JSON file with your application. So if your application goes down, so does your data. Making a database sort of serves as a uniform place to keep the data away from the application, and that's separating your concerns so that if something bad happens, your app goes down, you don't lose the data too, right? We're also going to be talking about data synchronization between clients. In the case of like desktop apps, for example, if you store that JSON file is being stored on each machine locally, every single person that has that app. But in some cases, you want all of the data in one spot. That's an obvious choice for databases. Also, large amounts of data. If you think about it in terms of runtime, how many people have taken CS1 or beyond? Okay, about half the room. So we can still consider runtime conceptually before then, but if you think about it, using these big JSON objects is going to have a lot of operations and a lot of complexity that can get really out of hand when you have a lot of data. Specifically, if you're trying to search, maybe for example, we'll see it soon, but let's say you have a user JSON file and it has some friends in it. And what happens when that person's really popular and has, 10,000 friends, 50,000 friends? A lot of the in-place sorting stuff or like searching to go ahead and find a friend, you're going to get kind of like an O of M behavior there. So there's not a lot of optimization in terms of finding and operating with the data. We're also going to talk about, like I mentioned, optimized data operations. We're specifically going to dive into the acronym CRUD. How many people have heard of CRUD before? You don't need to know what it means, just the acronym before. Okay, cool. And then also, we're going to talk about a little bit more about like server runtime environments and stuff like that. The biggest point on there is, depending on where you host, for example, Vercel is one of the hosting options that a lot of people use. You're actually kind of on a partition of their servers, and you don't even have access to file write to begin with. So if you wanted to dump your data as a JSON file and write to the local machine, you can't. They don't allow you to do it. So there's a lot of restrictions for servers as well. So for the case study, for the rest of this, we're going to be talking about Minecraft servers because I feel like it's kind of just very comprehensive. There's a lot of complexity there that you wouldn't think about. We're going to talk about it in terms of Minecraft servers. So with that being said, we're going to set some ground rules for what we want in the server. So we're playing with 10,000 concurrent players. It's a good amount of people. Each month, though, we're going to have 1 million different users. So obviously not the same person who's going to play for the entirety of the month. We're going to have 1 million different people pass throughout the month, but 10,000 active at a given moment. Each player is going to have progression. So you're going to have to store data for all of their progression, whether that be their rank, their plugin state, all of those different things. We're going to need to store data there. We also want to store some other things. We want to know their currency. We want to know their perks, their friends list, what factions they might be in. And then for each of the factions, who's in the faction, where's the faction, who owns the faction. So as you can see here, there's a lot of different pieces of data. And on top of that, they kind of have this really nested relationship here, right? We have players who are part of factions, all of those type of things. So it's a little complex. Each of those bullet points you can kind of consider like indentation, a relationship. So this is the big JSON file that I mentioned, okay? We can try to store everything here as just a bunch of JSON files on the local system. But as you can see here, this can get really out of hand really quickly. So basically, if we are using JSON, we're just limited to a bunch of arrays, really. If you look here, users, right, we have, so like for example, imagine that this is representing a message. This message text is hello world, someone started, etc. But when you start looking at the reactions here, things can kind of get crazy. So reactions is an array of different types of reactions, and each of those then have all of these fields. But if you think about it in terms of the users, if you get a lot of likes on YouTube, you now have that massive array associated with one message, or one video, rather. That relationship isn't very optimized, and again, if you're trying to figure out, like, did user 7 like post hello world? You then have to go grab hello world, and you have to search for that user in this big long array. And in this case, it's convenient enough where it's sorted, but in most cases, it won't be sorted by any rhyme or reason, which completely eliminates all of our optimization for searching, like binary search, etc. Right? So there's definitely some big drawbacks there. So we don't want to use one big JSON file, but funny enough, that's actually what NoSQL is, with a lot of big differences and benefits and advantages. So I'm going to introduce you to something called Firestore, specifically one of the few, or not one of the few, one of the many NoSQL databases. And what NoSQL databases do is it removes the part of the file writing. So really, end of the day, is just a bunch of JSON files, except those JSON files are stored in a server, and you can access them through all sorts of different operations, particularly like get by ID, all of those types of different things, right? So there is some truth to the whole JSON thing. It actually is pretty good for some specific instances, and I'm going to go over those in a few slides, right? But I will say that I did adapt these slides from Nick, our last president, and he didn't really like Firebase very much. So I left this quote here from him. While it may seem like this is a poor idea that should never be approached, it really depends on the use case. Does it have the second quote? No. He said, people treat Firebase like a hammer and every problem is a nail. So definitely be a little cautious when approaching NoSQL databases. I'll go into why in like a few slides, but this is kind of what you can see here, right? So it is just a bunch of JSON. But I'll go into what makes a NoSQL database better than just using JSON on your server. There's a lot of good benefits there. So the other thing that we can do is we can use a relational database. I'm going to be talking about SQL. And the reason why relational databases are very cool is we can actually represent, we can ensure that all of the user data can be stored in a schema, which is essentially the shape of a blueprint. And then that storage solution, we're able to represent relationships. So like, for example, instead of having just a big long array, we could then have keys that are just almost like an O of 1 access between the two objects, however you need. So like, for example, I'll show it later on, but so we're going to talk about which one are we going to use. In this case, we are going to end up using SQL. And the reason is because, like I said, SQL is best for relationships, for deeply related pieces of data. And that's what SQL accomplishes. And as you can see here, there's kind of a lot of stuff going on here. And we actually represented it on this slide. So for example, we have friends, we have a profile, who then can point to multiple friends related to multiple faction members and the faction. So all of these things here is essentially what SQL is going to be very, very good for, is keeping track of those nested relationships. So now we're going to talk about comparing the two. The biggest question is what is faster, but I'd say what is just some of the pros and cons in general. So I'm going to go into that a little. So they are largely equal on average, but they both have their very specific pros and cons for their very specific implementations that you need to consider, right? And this is a really good concept to talk about in like system design type of technical interview things, is even just having the consideration of picking a database shows a lot of insight in terms of technology. So I'm going to talk about all of the pros for SQL first on the left. As you can see here, there is another acronym called ACID. I'm not really going to go into that because it's a little out of scope, but essentially what ACID is saying is that there are a lot of fail-safes in place to keep your data secure. So there's a lot of investment in data integrity. What if it loses internet in the middle of running? What if it loses power, right? What if something actually happens to the server? There's a lot of ways that are invested in trying to keep your data in one piece. We also have simple keyword queries, which I'll show in a few slides. There is also long-standing community support since SQL has been around forever. There's a lot of open source technologies. So this means it's pretty easy to host your own SQL database. It's pretty easy to Google how to query it. It's pretty standardized since it is open source, right? And a lot of forks of it is, at least. A lot easier to self-host. So some of the cons, which I'm going to go into the next slide, it scales vertically. And I'll describe what vertical versus horizontal scaling is in a second. This isn't a concept that is particular just to databases, but it is an important concept that does relate to databases. And then some of the other cons, it slows down as it gets really big. So SQL does hit diminishing returns as you put more and more data into it. It sort of has a logarithmic curve in sort of performance. And it does require a lot more planning. As you can see here, you need to have all of these things defined as you create your tables. Adding and removing keys while you are in production can be a nightmare. You can accidentally drop tables. If you signed up for Night Hacks on July 7th from 7 a.m. to 11 p.m., you'll know what I mean because we accidentally dropped the entire database by adding a key. So it is a little hard. Thankfully, we had backups, but it does require a lot more planning, right? You do need that level of foresight and understanding of what you're building when you're defining your tables and your schema before you get in too deep and make a mistake that is just going to delete your data. So a lot of SQL also has built-in backups that you can implement, so they kind of consider that. As for NoSQL, here's some of the pros. It's about as fast on like a normal size data set, so a billion data sets or billion pieces of data and less, but it is significantly faster for larger data sets due to the horizontal scaling I mentioned, which I'm going to go into on the next slide, right? The biggest thing about NoSQL is that it's distributed. That kind of goes into the essence of the horizontal scaling. Since these pieces of JSON are not related to each other in many ways, because if they are, you really should be using SQL, you can almost you can put the JSON wherever you want. You could throw it on that server, on this server, on that server over there. You could throw it on whatever server it needs to because it doesn't need to be like living next to the other data because it's completely independent of it all. So that's what allows it to have those distributed systems. And what I mean by that is, I'll go into that in the next slide. I don't want to spoil the surprise. It is also stable, and because it's distributed, which I'm going to go into in the next slide, it makes it better. Usually for NoSQL, you store it on multiple servers, and I'll explain why in a sec. But that means if one of the servers goes down, only the data on that server is affected, right? You could be fortunate enough as a user to be on the server over there that's still up. So what that helps with is that you get little downtimes versus if a SQL server goes down, it's all down. The data will be fine. There will be backups. It'll be safe. But once that SQL server goes down, everything goes down, right? So that's another benefit of NoSQL. It can also store unstructured data. So you don't need to worry about all of those different kind of complex relationships. All of that should be fine as is. So some of the cons, there is no standardized query language. All of the flavors of SQL use the same commands, almost like a programming language. NoSQLs, they are newer, they're a little more opinionated, and it really depends on the framework by which you're using it, which can be a little hard because that means every time that you swap to a different NoSQL solution, you're going to have to, in essence, learn the programming language again, right? So Firestore and Mongo are not the same thing in terms of how you actually use them in code. Even though the way the data is represented is very similar, it is not the same thing, right? So that's definitely a big con. They are usually less efficient than SQL as well. The queries are not optimized very well. It's kind of just grab the ID, look for the ID, that's that. It does help in the fact that it's distributed. So like, for example, if you have 10 servers, it tries its best to balance, most clients will balance the load between all of the servers. But once that one server in itself gets full is when you start seeing those performance losses, right? And then the third one, which is a bit interesting, distributed data being in different servers actually makes it really hard to work with contract work, specifically government or banking. Because if you think about it, a SQL server is just one server. We lock it in a room, put 400 missiles in front of it, and no one's going to touch it. The government likes that. But with a Mongo server or any sort of NoSQL, you have multiple data centers all across the world that are distributed, and that becomes hard to kind of put into play, kind of guarding all of those, right? Another thing is you can self-host NoSQL, but that completely defeats the point of what it's for, which again, I'm going to show right now. So we're going to talk about horizontal versus vertical scaling. This is really the biggest thing to consider when you're choosing a NoSQL solution, because at the end of the day, in my opinion, NoSQL is not fun to work with. It's bad. But there are specific instances, and this is that specific instance, right? So what horizontal scaling is, and this doesn't just apply to databases, this applies to anything that you make in software. Horizontal scaling is when your resources run low. Like let's say your server is running out of CPU, running out of GPU, running out of RAM, all that type of stuff. If the resources run low, because horizontal scaling is just buy another computer and find a way to sync them up to work together. That is a lot cheaper. Because if you know anything about technology in terms of hardware, there's a logarithmic curve in how much money you can throw at a machine. The difference between a $2,000 graphics card and an $1,800 graphics card is a lot smaller than a $900 and a $2,000, right? There's kind of a slowdown in terms of hardware. So there's an upper limit you can hit in terms of performance. Buying a whole new system is a lot cheaper per unit than it would be to just throw more money at the GPU, throw more money at the CPU. So this is definitely cost effective. The only issue is that you need to find a way to synchronize all of these systems to work together. That's hard in a lot of cases. Why is that helpful in NoSQL? Because the data is what? Doesn't depend on anything else. There are no relationships. It can be on its own server, doesn't need to care much. The synchronization in a lot of NoSQL servers is just the little client that's like, oh yeah, let me remember what server that's in, and then send them to that server and then retrieve, right? So the synchronization becomes easy for NoSQL databases. So like I said here, it's ideal for independent systems. So then on the flip, vertical scaling is just throwing more money at the hardware. If your thing is running low on resources, just buy more RAM and smack it in there, right? Try to make it work. This is very costly. If anyone's tried to upgrade their computer for any sort of restraints, just upgrading in general is a lot of money. Imagine in terms of a data center. It can get really out of hand. And there are some projects that are trying to do horizontal scaling with SQL databases, but that's kind of like last 3 to 5 year kind of technology. So it's still kind of experimental, right? But vertical scaling is basically saying it's one system, everything's on one server, and that's why there's a lot of vulnerability in the fact that if it goes down, the database is down forever. And it's costly, it's very expensive at a certain point. And so this is just another kind of graphic to kind of show the difference between vertical and horizontal scaling, right? As you can see on the horizontal scaling, we just buy more machines, but in the vertical scaling, we're getting bigger and beefier computers each time that we try to upgrade, right? And so that again also kind of creates that migration issue of like, once we buy the new system, you have to move all the stuff over, there's downtime, there's stuff like that. So that's probably, I might be biased, but probably the only benefit to NoSQL. I don't think there's any other benefit. And I think the way the data is structured is hard to work with, but when it comes to large amounts of data and the horizontal scaling, it is really nice. It is really nice. libSQL is a project that's currently being worked on that is trying to make SQL distributed horizontally, and it's actually going really, really well. So I may take that back and say that there's zero benefit to NoSQL soon, but that's kind of where we're at right now. So we're going to talk about a little more complexities of each, and then we're going to talk a lot more on SQL, right? So what is a non-relational database? These are some examples I was talking about. DynamoDB from Amazon, MongoDB from, well, Mongo, Cloud Firestore from Google. All of these are different options that you have for non-relational databases. So it's an approach to storing data that isn't based on tables like SQL. It instead is focused on a model, right? So here's an example. On the left-hand side, this is a model. You can almost consider a model like a blueprint, kind of like the constructor for an object or a struct if you've taken, most people have taken C in this room. So kind of like a struct, right? It kind of defines the shape that all this data that's going in is going to be shaped like. And once a model is instantiated, it turns into a document. So this right up here is an example of a document. It's actual data that's been populated. And this down here is an example of a model. So then all NoSQL databases really are is documents, a group of documents that are the same shape. It's called a collection. And so a NoSQL database is a bunch of documents in a bunch of collections. And that's essentially what a NoSQL database is. Instead of having tables that define things, we just have kind of like, almost like drawers, where you just grab a piece of paper and pull it out and you expect it to be in the shape that you want, right? So there isn't much relationship, there's just shapes. That's all I'm gonna go into on NoSQL. I don't really think NoSQL is, the other reason I don't really wanna go into it is because I could teach you all Firestore right now, but then you're gonna wanna use Mongo, and then Mongo you're gonna have to learn the new programming language. Like I said, it's not very standardized in that sense, so I'm not even gonna bother. That's all you need to know about NoSQL. Does everyone understand the whole horizontal scaling and why that makes NoSQL better? good, because that's a really important concept that I got out of this when Nick did it, and it helped me a lot. So I'm going to talk about relational databases. We're specifically going to focus on SQL. So there are a bunch of different, you guys are probably going to ask, there's a bunch of different flavors of SQL. There's Microsoft SQL, there's Oracle SQL, there's MySQL, Postgres, SQL, all of these different things. A lot of them are just open source forks of one another or little side projects that split off. A lot of them have their very nuanced differences, like the way they handle date objects or serializable objects, stuff like that. But at the end of the day, they are a lot more standardized than Mongo, right? Or something like NoSQL. The querying languages you're going to use is still going to be the same. They still do have their own independent nuances, though, that you do need to take into account. So the way that relational databases work, like SQL, specifically Postgres is what we're going to be talking about, it is in tables. It's a tabular format. And so the major difference is that we also have a specific type, which is called a key. And that key, if I can go back here, is what we see in this, right? So the entry owner key, user ID key. Notice how they kind of have a linking property with one another. That is essentially what a relational database is we are making those relationships. And so we use keys to specify those relationships. So this is where we're going to get a little vocab heavy. SQL has many types of keys, but the only two that are the most common and the ones that we're going to look at, because there's a lot more that I'm not going to cover in this workshop, primary and foreign keys. So a primary key is a value that identifies a given row. It's kind of like your identifier. A foreign key is a value that points to another primary key. It's kind of like the pointer where the key is the value, right? So that's kind of the idea that we have here. So let's take a look at a real SQL database. This is, for those of you who don't know, our former president, Nick, he has a game studio. And this is kind of just a very simple, high up level of what his relationships look like internally. So you can have one of your different profiles, whether that be from your Apple, Meta, or Steam, because they're making games, that then points to your table-bound profile, which is the name of the studio, your actual profile for them. And then from there, you have the people you've blocked, you have the people you're friends with, you have your other guild members, and then guilds are their own independent tables that point to all of that. And you can kind of see that relationship here with all of the different keys that you have set up, right? So that's kind of an example. You could try imagining what it would be like to implement this with JSON objects. It is going to get pretty crazy pretty quickly, which is why we probably don't want to use NoSQL. So here is kind of what a SQL database would look like. You have the columns, which essentially serve as the type, right? You can see here some of the things you'll use to look at them will say like key or whatever. It doesn't really matter too much. Just the idea is that these are the types. And then each row is almost like similar to a document. It is actually a piece of data. So each column is the types, and each row is the actual object in that table, right? So as you can see, you have your ID, your username, and your BIOS, right? Your action, whatever, blah, blah, blah. So like I said, columns acts as our types. Rows are the actual data. That's why we call them tables, because they're comprised of rows and columns. And so I'm not going to spend too much time on this, but if you want to use, I've used it, we're using it on the dev team. It's a tool that you can use to create all of those cool diagrams. So if you're trying to plan out a project that wants to use SQL, I probably honestly do recommend doing something like this. I've used this. I've used Excalidraw. I'm honestly more of an Excalidraw fan just because it's fun. But it definitely is a good idea to take some time before you start your project and start figuring out the way you want your data to look. Because like I said, migrating, especially when it comes to changing keys, is a pain in the ass. So you might want to start looking at ERDs ahead of time. So this is where we get back to that acronym I talked about. CRUD is essentially, it's not just SQL dependent, but we're going to look at it through context of SQL. This works for any database. Doesn't have to be SQL or NoSQL. It could even be one of those fancy databases like storage buckets or KV or whatever, which I don't really get into here. But CRUD essentially is the concept that data should be able to be created, read, updated, and deleted. All databases fundamentally should be able to have those capabilities, because if they don't, why are you even calling yourself a database? These are just fundamental. You need to know how to do these, right? They need to be able to be done. So we're going to look at CRUD through the context of SQL, specifically PostgreSQL, right? So I'm not going to go super deep into the commands. What I've done ahead of time here is I've created a start database script. I am not in the right directory. Hold on. Workshops 2024, hello world, databases. Okay, so I've created a start database script. Essentially, all this does is it's going to set all of these parameters for me. And this is going to be in the GitHub repo. This is only going to work on Linux systems. Sorry, not sorry. But if you're on Windows, install WSL. Thank you. Basically, all this is doing is it's saying, hey, do you have Postgres installed on your system? If not, install it. Then running all of these different commands, it's saying, we're going to create the database. We're going to give me admin privileges. And then we're going to make a table. We're going to make a database called NiHacks. So I'm going to go ahead and run the start database script. And now, as you can see here, I actually have a database. It doesn't look like much, but this is what the database looks like in terms of running a terminal client. The database is up on my local system. It's on one of my system ports. I'm pretty sure, I don't remember the default port for Postgres, but if I had an application, I could connect to this with localhost. I could go in my environment variables or whatever and set database URL to localhost/port, whatever. It's up, it's running, it's online. I'm not going to show you how to implement any database connections on a Python app or a React app or anything like that. Just conceptually speaking, the database is up, and this is what would be able to be accessible to any client that you have, Python, etc., right? So when I look in here, I can go ahead and look at all of the tables by doing or all the relations by \DT, but as you know, there's nothing in here, right? So going on forward, this is another important one. So this is where that kind of variance comes in, especially between different types of SQL, is how they handle types. I like Postgres, pretty straightforward, but if you try taking a date object to MySQL, you're gonna have to put it in a different encoding. Don't even ask about dates in libSQL, it's not something it supports. So it's like, this is the type cheat sheet for Postgres. And so there are different types. I know most of you have gotten through Intro to C at the very minimum, or in it right now. You know the difference between an integer and a float, and a double, and a string. Well, unfortunately, for whatever reason, those do not one-to-one convert to SQL. They have their own type system that you're going to need to learn, but most of them are just a one-to-one comparison. As you can see here, a string, instead of it being called a string, it's called a varchar. It's like variable characters, right? And instead of a long, it's called a big int, but it looks like big int. But that's basically how it works, right? And so let's kind of do a little bit of SQL operations. So I kind of did this already. That was in the script, right? I did create a database called NiHacks. How do you know? It's because we're in NiHacks right now. And then how do we know we're in it? I said use, now we're in NiHacks, right? That's kind of just what it's saying here. All of this kind of jargon over here. And then what we can do, let's go ahead and let's create some profiles. So I'm not going to copy and paste this. I'm going to keep going back and forth. Let's see. So we can do create table profiles. And then we're going to essentially, in the parameters, we're going to open parentheses and say all of the different columns we want, all the different types we're going to specify. So we're going to do a first name of variable character length. And for the most cases, this is going to be 255. That's because that's right at the end of memory before you start taking up more. And then we're going to move to last name, also going to be varchar, 255. And all of your statements in SQL are going to have to end with a semicolon. If I press enter, nothing's going to happen until I hit that semicolon. It responds back to me, says, hey, we've created table. And now I should be able to do /DT. And as you can see, we now have a table. That table is going to be profiles. And just like that, we now have our first table. So we essentially have one of these now in our database. It's completely empty. We're not going to be able to see anything for it, but it's there, right? There's just no data in it. We only have the columns in there. So to create an entry in the table, we're going to need to use what's called a statement. A statement is the same thing as a command. They just like calling it statements, whatever, right? So when we use these, we actually already used the statement. We used create table, right? So we're going to use statements to kind of perform all four of the CRUD operations. So this is the C in CRUD. This is going to be creating data. So what we're going to do is, for the first time, we're going to insert something into the database. So the keywords are going to be in capital, by the way. That's just the standard for SQL querying. All of your reserved keywords, kind of like int, double, function, def, like all of those like specific reserved words are going to be in all caps. So we're going to say insert into. We're going to pick the tables that we want, and then we're going to go back here, and we're going to say what columns we want to actually insert into. If you, what's up?
Is SQL case sensitive?
So it's not, but it's best for like standards to use capital letters on those things, because then it helps you, like, because sometimes There are SQL engineers. There are people who literally do this for a living. What does that tell you? There are some SQL queries that are like pages long. This is some bullshit. So like when you're proofreading that and debugging, it's going to be really helpful to know which one is reserved keywords that you're using in commands and which one's the data you're putting in. So it's best practice, but it is not like explicitly case sensitive. Another thing, we want to specify what columns we want to insert into. For example, last name, currently, we didn't say that it's required. You could put in someone in the table with no last name. So we need to specify, hey, what fields are we inserting to? We're inserting first name, we're inserting last name. And then from there, what do we actually want to put in? So we're going to specify the values. And then another thing about Postgres that'll might throw you for a loop if you're doing it this way, you're not allowed to use double quotes, only single quotes. And by you, I mean me. I did that the other day. So single quotes, we're going to go ahead and insert myself into the database. And boom, we've now inserted into row 0. And so we're all set there. Now, if I go ahead and do, actually no, doing /dt will only show me what tables exist, but I'll show you how we can read, right? So here's how we read. This is the R. This is how we retrieve data. So the select keyword is going to be kind of our main driver for reading. And from there, we can use wildcards. We can use a star. So we can say select star, which in SQL is basically all. Then we pick which table we want to pull it from. We want all from profiles. Just like that, we now read. So if we want to go back up here, and let's say, I'm going to insert my mentees here, 2 of them. You guys made the bit, right? So we can insert here, and then and if we select all from tables again, we now see that we have multiple people here, right? Pretty cool. So this is just writing raw SQL statements, and it doesn't look like it's anything great, but there are things out there to create connections programmatically to do all of this for you, right? So this is just conceptual again, but we now have a database, right? This works. So we've now done create, we've done read, but what happens, for instance, let's say, one of us gets married and wants to change our last name. How are we going to update all of the data? So that's what they use for. I'm not getting married. I'm going to update myself to Mr. President because I think my name, I should have the cool name in the database, so I'm going to update, right? So here's how it's going to go. Oh, I didn't talk about conditionals. So obviously, we don't want to select all. That's never great. We don't want to select all from the database. So we have conditional keywords. So we can basically specify the command. So we're going to say select star from profiles. So we want to grab all of them at first, but we only want ones where, and that's where this keyword comes in. So this is where we can specify basically a ton of Boolean values to just if else our way through, right? So for example, we want from the profiles where first name equals Dylan and last name equals Vidal. So this should only give me back. And as you can see, it's retrieved that specific row. What if we wanted me or last name, Daniel's last name? Just like that, we now have 2, right? And there's a ton of different conditionals that you're going to have to learn. It's its own syntax. You could say where first name starts with L. There's a way you have to learn how to do that. I'm personally not super in touch with SQL statements because of what I'm going to show you at the end. But all of these things, like proof of concept, it works, right? You're able to update and you're able to conditionally query. So now we're going to talk about update. Like I said, I want to change my name. I want to be cool. I want to have all caps be Mr. President so that when you query the database, you know who I am. So that's where the update keyword comes in. We're going to say update. And again, we're going to say profiles. So we're going to update in the profiles, and we're going to set the first name to Mr. We're going to set the last name to President. Now, if I called this, it would actually update every single row to this. Kind of crazy. We don't want to do that. So again, we're going to specify where. If I didn't do that, people have done this in like real prod databases. They forget to put the where, and just like that, you have now set every single user to the same dude. Imagine being at work and doing that. That is why SQL engineers exist. There are people who get full-time jobs to do this on legacy systems. Thankfully, a lot of companies have evolved, implemented new tech that stops you from doing this, but know that it is a real thing. You can update every single person to be the same guy. So I'm not going to do that, all 3 of us. That'd be so tiring. We're going to do where first name equals Dylan, and last name equals Vidal. Oh, I forgot the semicolon. There you go. So it's updated. Now again, if I do select star from profiles, just like that, I'm now Mr. President, right? So you can see there again, we got the update. Things are looking pretty cool here. What if, say, for example, I wanted to do something different? What if I wanted to do, we're going to set first name to Night Hacks, where the first name equals last name. Now we can go ahead and update Carlos's first name. And then we pull from profiles, and now his first name's Night Hacks. Congratulations. But see, we kind of have these different queries we can do, different conditionals, kind of handle everything that way. Pretty cool stuff. The last one is going to be delete. So, same thing as select, but I'm going to, again, point this out to you because it's very important. I want to show you something crazy. Nowhere. It just deleted everyone. There's no one. So notice how that where is very, very, very important. Okay, I'm going to go back and go ahead and insert everyone back just so we have the data to mess around with. But yeah, no, SQL's fun. SQL does not have any safe holds for you. I'm going to go back and do Mr. President.
It does, if you go back, you can roll back and come in.
Yeah, you can, but here.
I know for the sake of...
Yeah, I'm just going over it now. So that's kind of the idea here. We can go ahead and run this. I don't really want to delete myself. We've seen wheres. I already did delete myself in the rest of the database, but here we go. We got next. And so to specify a particular column as a key, we're going to use something called a constraint. Essentially what it's saying is we only want to look at this specific kind of window of things. So here's what happens here, right? So remember, when we create tables, we want to specify what type we're going to use for each of the columns. We did that earlier, back here, right? We created the table profiles, and we had first name and last name as our columns. Well, if we go back here, we now have a new thing here. So along with our data type, we're going to specify primary key. So we're going to create table faction, and that's going to have a faction ID that is a big int and a primary key, right? And then we're going to have the name of the faction, which again is going to be a varchar of 255. So we created that table. So now what is this primary key and what is it going to do? So foreign keys are a little more complicated, but they're what's really connecting those relationships, right? So these are three commands, but what these three commands are going to do is essentially create this, right? So we're going to create table. I actually just created that last one for no reason. I'm going to drop the table factions here. Drop table faction. Dropping a table is just getting rid of everything, by the way. You just get rid of it. So we're going to create the table of users. So we're going to create table users. We're going to do username of varchar 255. That is going to be a primary key. And then we're going to do money of int here. Right, so now we have our kind of like Minecraft users getting rid of profiles, right? So we've created that table, and then again we're going to create table factions, singular faction, and we're going to do the faction's leader, right? Who owns the faction, and then the name of the faction itself. And so now we've created both of those tables, right? We can prove that by doing this. We see all of our tables here. Right? And so what we're going to do is we're going to say that the faction leader, we're going to create that foreign key, and it's going to go from leader, and it's going to point at the username. So it's kind of going here, right? So the leader is then this username. So we'll go ahead and run that. Constraint, faction leader, foreign key. It's going to go to leader. It's going to be referencing on the users table, so specifically saying what table to look at. It's going to be referencing the username. I don't know why there's two parentheses there. Did I spell constraint right? Constraint faction leader, foreign key leader, references users, username. Odd. Well, I don't have anything to.
There's a parentheses at the end.
Yeah, I don't think I need that. I might be crazy. Yeah, no. Did I spell constraint wrong? I think that's how you spell constraint. Syntax error at or near constraint. It doesn't really matter. I can Google that another time, but we're not going to be doing anything after here. I'm just creating that relationship. So, actually, it's a lie. I did want to show a join, which I'd need the primary key set up. Hold on. I'm going to Google this real quick. Set constraint SQL statement. Also, you know it's old when IBM has the tutorial up. If I can't find this, then I'll just describe the next parts conceptually. I don't want to hold up too long. Oh, I think I need a set constraint. Okay, well, I can't figure that out. It is what it is. We'll move on. I'm going to Google that on my own time, but I'm not really, like I said, I'm not super in deep with the SQL statements just because I use ORMs, which I'll go into at the end. But what we could do, we're going to talk about joins, which is kind of like the last thing about SQL. It's going to be what happens when you want kind of, we have all of these relationships for a reason, right? What happens when we want to know, grab the username that is the leader of this faction, right? We're going to need to do something like that, right? What's up?
I think you need to put set constraints, like with an SF after constraint. No, because we said that. Oh, that was another.
Yeah, no. If anyone wants to figure that out, then y'all could do that while I'm talking. But what we want to be able to kind of abuse or utilize, rather, these relationships to query our data. So like what happens, for instance, if we want to find factions or users that are leaders of factions, right? So we need to have a way to kind of make those queries. And this is where a lot of those optimizations come in. If you're using MongoDB, what you would do is you would grab a faction, grab that leader, make another query for every single faction to then go to the leader, right? So this is where SQL joins come in. And this is where that optimization comes in for all of those really complex things, is it's just going to be one query, said and done, send over in the exact kind of shape that you want in that complexity, right? So remember how I said they're SQL engineers? 85% of their job is writing joins. It's because 85% of the complexity of SQL is probably going to be writing joins. There's a lot of stuff that can kind of like, a lot of complexity in it, right? And so we're only going to look at one type of join for the example of this because it's kind of the easiest to comprehend. And then I'll talk a little bit more about other stuff, right?
I think I realized what it was.
What's up?
You didn't. So you have to you're altering the table.
Oh, I had to do that on instantiation.
You have to alter the table first.
Yeah.
Because you didn't make the constraints in the table. So
I forget how to add a key. Is it alter?
It's just alter table and then you add the constraint. You alter table and then add constraint. And then foreign key.
Do I do set constraint? Alter table.
Add constraint because you're adding it.
Right. I think it's faction. There you go. Awesome. Thank you so much. So we now have that relationship set. And then we can actually use that to kind of demonstrate the joins here. So we have here all the different types of joins. You can consider them like Venn diagrams. What a join is going to be is we're going to be grabbing data from two different tables. And how do we want to recreate that relationship? It could be a left join. It could be full outer joins. And all of these have hundreds of pages in and of themselves. You can kind of get them pretty simply, some of them, but others are kind of just like interesting. And so the one that we're going to talk about is inner join. It's essentially going to be grabbing from both of the tables where there's a relationship. So here's kind of the example that we have here. Remember, we have our profiles here, or the users which we created that has the username and the money. And then we have leaders, and these are the factions, right? So what you could do is you could say, we're going to select these fields. So we're going to select the username of the profile, the name of their faction, and their money, and we're going to grab it from profiles and factions where they equal each other. And so like I said, notice how this is a lot more complex than our last few queries that we've been doing. So what we could do is we could do insert, we could go ahead and insert into the factions table. We're going to go ahead and insert all of the like users here. So we could do insert into users. Yeah, insert into users. And we could do, here, let me just do this up here. Like I said, my good old SQL is not great. So we could do, we can insert into the faction. Actually, it's going to be the users. And users are going to have the username and money. So let's kind of do this. Let's see. We want to do, let's do Nitro, because Nitro has a lot of money. Right? We can go ahead. Who else should we insert? We're going to insert Carlos again, but he's going to be broke. We can insert me. I'm going to be slightly above broke. And then we can go ahead and do the same thing for our factions. I'm going to be the leader of Nighthacks. Thanks, guys. And then, what is it? The faction is leader and then name. Right? And then we could say, who else wants to lead something? Nitro can lead UCF. So right now, we have users. Huh? Oh, I didn't do the semicolon. Whoops. So we have all of our users here. And then we have our factions. Right? This is kind of the table that we have represented here. Right? And so what we could do is we could, again, write this join. We could say select users dot username. The users, I always forget if I add the S or not. Okay, well, it'll be users dot username faction dot, we said that was just name, and then user dot money from, and this is where we're going to create that overlap. So we're selecting it from profiles and factions. So that's the inner join, right, the overlap. And then we're going to do provide inner join factions on profiles dot username equals faction dot leader, and that's not profiles. I changed it last night to user, right? And it's actually user as I scrolled up. Kind of see that. So this is creating that inner join based on that relationship. Oh, semicolon. Users dot money faction dot name from users. Yep. Should be faction. My S consistency is not great, but there you go. So we've grabbed people that are leaders of factions. So as you can see here, me and Nitro both lead factions. So we've grabbed us two. We got our names here, and then we have our money. Nitro's a lot richer than me. But this is essentially what the joins are, right? And this is how we can then create those really complex queries. So that's kind of the end of the conceptual stuff. Now I'm going to talk about more about application very lightly. Again, I don't have time to go super deep into everything, but essentially the way it's going to work is going to kind of be like a 5-step thing. You're going to first have to consider what database you want to use. Same thing we talked about earlier. Do you want SQL? Do you want NoSQL? Do you even want either of those at all? There's a lot of different databases. Some complex applications will even need multiple types of databases. You might need some type of bucket storage. You might need some KV, any type of stuff like that. But you start by picking it. Then you're going to find a host. You can host that wherever you want, right? You can find your local machine. You could do it on a private server, or you can find a managed provider. I know like Vercel has a database, AWS has a database, everyone got a database. I'd really recommend Terso. Terso is really great to get started on projects in libSQL. It's like 10 gigabytes free, something like that, pretty good. And it's SQLite, which means your data is super tiny, so 10 gigabytes will go forever. And And then you're going to kind of research the clients for your framework. All of the different kind of things you're going to work with are going to have different clients, right? If you're trying to do it from a Node application, it's going to be a different process than a Python application. But at the end of the day, you can get a client that essentially runs those commands that I've been showing you for you, right? And then you're going to create those connections. You're going to create all your functions inside of your code that you need, and then you're going to perform them whenever you want. Say every time you want to click a button, you want to add something to the database, you just write that function with that connection, do it as you need, right? And so the last thing I kind of want to talk about, it's like a 4.1 that I think is honestly why I've been so abstracted away from SQL queries, as you saw me struggle just now. There's another thing that's kind of coming up called ORMs. ORMs are really, really fun. There's been a lot of movement in web for ORMs. Essentially what ORMs are is they allow us to treat queries more like objects, because a lot of the code you're going to be writing is going to have like object-oriented paradigms. And so for web, there's things like Drizzle and Prisma, both really, really popular right now, making a lot of optimizations there. And then for like Python, there's like SQL Alchemy. They also have another SQL ORM that I'm not quite remembering because I don't use Python like that. But that's something that, again, I don't have time to go into, but I'd recommend you guys looking into ORMs. I know a lot of web frameworks have them built in already. I know T3 is opinionated. You can have either Drizzle or Prisma already, like all those type of things. So I'd recommend looking into those. With that being said, that is it. That's all I've got. Kind of dove into everything conceptually. I'm going to pull up my QR code for the workshop because I forgot to put them on the slides. But yeah, that's about it for the workshop. Thank you. I'm going to end the recording now.